Hello, welcome to the third part of economic feasibility assessment. In the previous two parts, you have learned the present worth and the annual equivalence analysis. In this part, we will explore the rate of return analysis, a key to measuring the profitability of an investment by calculating the internal rate of return. Rate of return, or ROR analysis method is favored by many managers over the present worth or annual equivalence methods. The key appeal of ROR lies in its intuitive nature. It measures the profitability of investment as a percentage, which can be more relatable than absolute dollar values. Understanding ROR is crucial because it offers a different perspective by emphasizing the rate of return an investment generates over time, making it easier to compare against a company-required rate of return. It is important to note that ROR is known by several terms that you might encounter in various financial contexts. The first is yield. For example, yield to maturity, which is commonly used in bond valuation. This represents the total return anticipated on a bond if the bond is held until it matures. The second, internal rate of return, or IRR, which is used to estimate the profitability of potential investment. Third, marginal efficiency of capital, which refers to the rate of return on an additional dollar investing in capital. Each of these terms, while related, is used in slightly different contexts to assess the profitability or efficiency of investments. Before we delve into the method for computing ROR, let's first distinguish between simple and non-simple investment, which is crucial for understanding how the cash flow structure of an investment can influence the complexity of rate of return calculation. First, simple or conventional investment. This type involves only one sign change in the net cash flow series over the investment period. We generally disregard any zero cash flows occurrence in this categorization. If the initial cash flows of an investment are negative, meaning you are spending money, these are termed the simple investment cash flows. Conversely, if the initial cash flows are positive, perhaps indicating incoming payment or savings, these are then called the simple borrowing cash flows. On the other hand, we have non-simple or non-conventional investments. These are characterized by more than one sign change in the cash flow series. Such scenarios typically emerge in more complex investment structures, where the cash inflows and outflows alternate over the period. Multiple I's, or ROR, indicating the points of cash flows inversions, occur only in these non-simple investments. Let's look at the table presented in this slide, which will help us understand how the sign changes in cash flow impact the classification of an investment. The first, the simple investment, so you can see the cash flow start with a negative sign in period 0 and 1, indicating an initial outlay or investment. From period 2 onwards, the cash flow remains positive, reflecting returns or benefit from the investment. There is only one sign change, from negative to positive, which is typical of a conventional investment. This single sign change simplifies the calculation of the rate of return, as the cash flows pattern is predictable and stable. The second one is non-simple investment. Here, the cash flow sequence begins with a negative value in period 0, turns positive in period 1 and 2, indicating earlier return, but then shift back to negative in period 3 and 0 in period 4, before becoming positive again in period 5. This pattern shows multiple sign change, a total of 3 here, to be precise. Such a pattern is characterized non-conventional investment where cash flows are more volatile and less predictable. So 3 major computational methods to solve the ROR, including direct solution, try and error, and Excel. Each method is suitable under various circumstances, depending on the complexity and the nature of the cash flow involved. For the first one, direct solution method. These methods involve mathematical formulas or financial calculators to directly compute the rate of return. It is most effective when dealing with simple investment where a straightforward calculation can be directly applied. For example, compute the ROR for the project A with the cash flow transaction shown in the table. In this case, we could easily solve for I star in letting future worth of the whole cash transaction to be 0. Noting that making future worth equal to 0 is identical to solving for I star in present worth equal to 0. And then we can directly solve for I star to be 10.67%. For the second one, try and error method, a practical and also widely used approach to find the rate of return, especially when direct solutions are not applicable or straightforward. At its core, the try and error method is an iterative process. For simple investment, the process begins with an educated guess of the potential rate of return. And using this estimate, we calculate the net present value of the cash flows. If the NPV does not equal 0, we adjust our guess depending on whether the NPV is positive or negative, and then we recalculate that. For instance, if the NPV is negative, it indicates that the guess rate is too high, so we lower it and compute again. Conversely, a positive NPV suggests that the guess rate is too low, pushing us to increase it. This adjustment continues until the NPV is very close to 0. Once the NPV value surrounds 0, where one estimate produces a positive NPV and the subsequent a negative one, we apply the linear interpolation to more precisely determine the internal rate of return. It is important to note that the try and error method is not suitable for non-simple investment where the present worth function does not generally decrease monotonically with increasing interest rate. For the third one, Excel method, which is a modern and highly efficient method for calculating the rate of return. This approach leverages the built-in internal rate of return function, which simplifies the analysis of investment cash flows. The syntax for the function is IRR, value and guess, where values refers to the cells that contain the cash flow amount, and the guess is optional, which denotes your initial estimate of the rate of return, which help Excel start the calculation more effectively. The Excel method is particularly valued for its precision and the ease of use, allowing finance professionals to efficiently evaluate the ROR of potential investment without extensive manual calculations. So in this slide, we will learn how to determine if we should accept or reject the project and how to identify the best project among various options using rate of return analysis. For this discussion, we will focus solely on simple investment due to the structure of our course. For decision rules regarding non-simple investment, I encourage you to look at the reference reading provided. Understanding the internal rate of return is vital but not sufficient on its own for making investment decisions for a single project. Firms usually aim for returns that exceeds simply breaking even. That is, achieving the net present value of 0, which signifies indifference toward the project. To ensure that an investment meets the minimum threshold set by company policy or decision maker, we use the minimum attractive rate of return (MARR). This rate represents the lowest return on investment that the company considers acceptable. Here's how we apply the rule. If IRR exceeds the MARR, the project is considered financially viable, and we should accept that. If the IRR equals the MARR, the investment yields exactly the minimum rate of return required, and we remain indifferent, neither explicitly accepting or rejecting the project. But if the IRR falls below the MARR, the project does not meet the required threshold of profitability, and we should just reject that. So now, let's turn to how we assess mutually exclusive projects. These are scenarios where choosing one option precludes the selection of the others, and it is essential to determine not just the viable project, but the best one among several alternatives. When comparing the projects, simply looking at their IRR is not enough. The project with the highest IRR might seem like the obvious choice, but this does not always hold true because IRR, being a percentage measure, does not take the scale of investment or the dollar amount involved into account. For example, consider two projects A and B. Project A requires an initial investment of $1,000 and return $2,000 after 1 year, resulting in an IRR of 100%. Project B, on the other hand, involves a $5,000 investment but yields $7,000, which translates to an IRR of 40%. If we were to decide based solely on IRR, Project A, 100%, would be the preferred choice due to the higher return rate. However, when we calculate the present worth of both projects at a given discount rate of 10%, we found that Project B, with a present worth of around $1,364, is actually more profitable than Project A, which has a present worth of $818. This example illustrates why it is crucial to use an incremental analysis approach. Incremental analysis compares the additional cost and the benefit of one project over another, rather than just their individual IRR. In the next slide, we will delve deeper into how to conduct this type of analysis effectively, ensuring we not only choose a viable project, but the most beneficial one from the financial perspective. Incremental investment analysis helps us determine which projects offer the better return on an additional capital required, particularly when comparing two mutually exclusive projects. In our ongoing example, comparing Project A and B, Project B is more costly than Project A by $4,000, but offers an additional return of $5,000. To analyze this properly, we break down the cash flows of Project B into two components. The first component is the base one, which is identical to the cash flows of Project A. The second is the incremental component, which is the additional investment and the return that Project B involved over Project A. To decide whether the additional investment in Project B is justified, we calculate the IRR on the incremental cash flows, which is 25%. These IRR need to be compared against the MARR. Here's a decision rule, similar to the previous we just learned. If the IRR of the incremental investment B minus A is greater than the MARR, it indicates that the additional investment does indeed pay off, and we should select the project B. If IRR equal MARR, the incremental investment just break even with our required rate of return, making either project equally acceptable based on financial return alone. If IRR B minus A is less than MARR, then additional investment does not meet our return requirement, so we should just stick with the project A. This incremental approach ensures that we are making the most financially sound decision by considering not just the total return, but more importantly, the return on the additional investment required by the more expensive project. Let's wrap up our learning of the rate of return analysis. There's one more to come for economic feasibility assessment unit. See you in the next part. Bye bye.